high latency, it means that the time it's going to take for processes to be executed and so on. So, and based on the paper, they claim that, with the NF virtualization, you can have up to like 200 microseconds to approximately 1 times 7 milliseconds. So now the recent research on reducing NFV latency. What causes NFV latency? Now you imagine you have a box, and then you're trying to share the box into like 5 different things, 5 different functionalities. And all these functionalities are running within the same box. Now each of those functionalities want to assume that they own the box, meaning that they have the access to all the resources within that box. Now with this being said, in the case of, well, let me just continue, otherwise we have 7 minutes. So the recent research, we have ClickMP. Now, ClickMP was proposed in CCOM of 16. And basically, what they did was they created a framework in which you can have virtualized elements, like network functionalities. And then we have NetBricks, which was in OSDI 16 as well. And all this, what they are trying to do is they are trying to accelerate the parallelism horizontally. And what that means is when you're talking about a sequential chain, you're talking about A connected to B, B connected to C, and so on. And where A, B, up until N symbolizes the network functionalities themselves. And as we're going to see later on, the main key observation, because there's been a lot of paper that worked on sequential, well, at least 4 papers that I've read, that worked on sequential chaining. Now, by sequential chaining, it means that it's ordered. So VPN comes first, before monitor, before firewall, before load balancing. And that arrow over there symbolizes a packet entering the network. So now the question is, what if we have a read functionality, say like a network monitor? All it does is it reads certain part of the header. And then right after the network monitor, we have the firewall that has the capability to draw packets. Now, if all these are in sequential chain, the question is, what can be the possible program, right? So the paper, they came up with a concept of parallelizing this network functions in such a way that they're trying to reduce the computational overhead. However, they ended up adding more to it, but we'll see how they resolve that. So now if we have a firewall and we have a monitor, and both of them are doing 2 completely different functionalities, what happens over here at the load balancer? We'll see that in a little bit. So, like I said, we have a packet, and if the packet originated from the ingress flow, entering the VPN, now it means that once it gets here, because it has been parallelized, what happens? We need to copy the packet in a way such that firewall can also have a copy of that packet, so as monitor. But the question is, at the end of the day, they both have different functionalities. If firewall drops the packet, and the monitor, of course, is only reading the packet, it's not going to make any difference. Now, what happens when it gets to the load balancer? So based on the paper, once firewall drops that particular flow, it will send a nil, just like a nil notification, to the next person, just telling the person that, hey, this particular stuff has been dropped. So now there is going to be an aggregation over here to tell if that particular packet should further into the network or it should be dropped. Now let's look at the interesting part. Now in this case, they call this a vertical acceleration as compared to the horizontal acceleration of sequential chain. So based on the paper, again, they claim that 25% improvement can be achieved by running NFs in parallel. And they also said that 53.8% of NFs can be in parallel. So we'll see the interesting part. Now, how does NFP exploit network functionality to reduce the latency involved in using NFs. So first, we look at the sequential chaining. Now, they first came up with a policy specification scheme. And with the policy specification scheme, they have 3 different types of policy that they use. The first is by ordering. Now, by ordering, here it's actually self-explanatory. Order NF1 before NF2. It means that NF1 comes before NF2. And then we can see an example of monitor and firewall. And the second part is parallel orchestration. The second part is priority. Now they use these 3 key parts as their policy specification. So in priority, what are we talking about? Well, in the case whereby we have the firewall drop a packet, and then once the packet has been dropped, it sends a nil packet to the load balancer, for instance. And the other one, the other NF, only read a substantial part of the header and then sends the message. The question is, how do we prioritize? Should we drop the entire packet, or should we still accept the packet in the network? And that's the parallel orchestration, where we have priority of NF2 is greater than NF1. And then we have the positioning. Now the positioning only deals with first and last. It's just to tell you what comes first in the chain and what comes last in the chain. So now the orchestrator design. Here we have all the 3 specifications they use for their policy. And at the end of the day, what are they trying to achieve? They're trying to achieve a service graph. Now, based on that service graph, which we'll be seeing in a little bit. Now, this NFP orchestrator is from the network functional virtualization architecture itself. And an orchestrator is just handling how things are being positioned in the network. So first, it does service graph construction, and then it does resource overhead optimization. Like I said previously, when we parallelize NFs, it means that we have to create other copies of that particular packet in order to have a copy of that packet in other NFs. Now, the problem with that is it's going to create a kind of computational overhead. Because you're creating another packet, you don't have to. We already have one. So what happens here, so this shows, how do you go back? Okay, I'm sorry, this is me not conversant with Mark. And so what we're trying to show here is, first and foremost, we have the NF dependency identification. How do you know that 2 NFs can be parallelized? Of course, you need to look into the dependency. The dependency in the sense that which part of that particular packet is each of the NFs interested in. Now, if the first NF is interested in one section of, say, like source IP address, and the second NF is interested in writing into the payload, there is no conflict. Because at that point in time, one does its job and the other does the job without changing the package itself, or the packet itself. And next, resource overhead optimization. Now, in this paper, they used what they call dirty memory reuse. Now, the dirty memory reuse is just saying that instead of having to copy the entire packet itself, you can take just that part of the packet that is needed by one of the NFs and have it read. You can create a link to just read that part of the NF as long as it's not writing to it. And then the second part is that once that particular packet has been read, it can be sent to another packet. Now, the concept they used here, which I'm trying to remember the name, they came up with a principle called correctness principle. Now, that principle states that 2 NFs can be parallelized only if both the execution and the processing of the packet by each of the NFs is not going to change the content of the packet. So for instance, if you have one packet entered through two NFs, at the end of the day, if the packet comes out the same, then that means you can parallelize the two NFs. But we're going to see that in a little bit. So the NF dependency, we have all these network elements, and I'm just going to run through this real quick. So here is just showing us that, for instance, we have the firewall, this is a read, and that's a write. So this is just showing the core network elements and what they do with the header and the payload, and also what action they can take. Moving on. So the NF dependency leads to the action dependency as well. The action in the sense that are we supposed to drop the packet, or do we allow the packet in the network? So first we have the action dependency analysis, which they carried out in the paper. So again, this goes back to what we've been talking about, read, write. So now if we have a read, I'm running out of time. Okay. So now if we have a read and write, if a read comes before a write, what happens? It's still the same thing as this, if it's being parallelized. Right. Now what happens if the write comes before the read? It's not the same packet anymore. And as such, the law or the principle of correctness will not hold in that case. So that's just all this is trying to show us, that if a write comes before a read, it's definitely not equal to what we have over here. So, moving forward, and actually that's the result correctness principle. Now this just shows the concept they used in ensuring that two NFs can be parallelized. Now if we have a read and we have a read, of course you can parallelize it because they are both doing the same action. Now if we have a write before a read, you can parallelize it. That's why we have this gray area over there and so on. So now the resource overhead optimization, I already talked about that, about they use the dirty memory reuse in their system, which actually reduces the amount of copy required within the entire network itself. And just going to move forward. So here it shows the service graph construction, which is actually the main concept behind the system that they created, the NFP. So here we have the first position, we have order, we have priority. Now how do you merge all this, which the system does have a compiler that compiles the policy, how do you merge all this into a dependency and copy necessity? Now by that we can see that what we have here, when it comes here, the NF1 is individual. So it means there's no dependency issue with the NF1. And then when we look at this, it does have a dependency issue with NF3 and NF4. And we can see that over here. And the rest, I think it's explanatory. Okay, so what exactly were they able to achieve with their research? So first, they were able to achieve resource overhead optimization by reducing the amount of packets being copied using dirty memory reuse. And also we have the NF runtime and the merger, which handles the packet delivery, the margin, and the dropping. So for the sequential chain, this is just showing the graphs that they came up with. Now their baseline study is OpenNet VM. Now OpenNet VM is another, I think it was published in 2016 as well. Now in OpenNet VM, if we look at this, we have this for the NFP, and we have this for the OpenNet VM. The difference between the two, real quick, is the OpenNet VM uses a core processor for each of the NFs, while NFP combines the entire NF together. So we can see that along the line over here, this shows latency, and we can see that NFP incurred a little bit of latency, more than the OpenNet VM. And that's only because of the processor. Now, they are using run to completion model. I can't remember, so just going to let that slide. All right. So now they claim that with increasing complexity of NFs, the performance becomes better. So here we have the latency benefit, and here we have OpenNetVM, we have the sequential parallel and the parallel no copy. So the parallel no copy is when the correctness principle is absolute, meaning that the NFs involved, they don't require any dependencies. They don't have dependencies. So, okay. So I'm just gonna skip that as well. It's just explaining the same thing. And here, still the same graph. This 1, 2, 3, 4, 5, 6 are shown over here. So the first one is a sequential. Okay. The first one is a sequential chain. It means that everything is running based on priority in orders. Now the second one, we can see that it has been parallelized. And if we look over here, the first one is OpenNetVM. We can see that our NFP sequential outperformed the OpenNetVM, and the rest can be intuitive as well. Okay. So in conclusion, they were able to come up with three major things: the policy specification scheme, the orchestrator, and the infrastructure. And based on their real world test, they were able to achieve 35.9% latency reduction. So that's and it's a very good paper. Now for the critique. So first, the first part talks about post-policy reuse. Now you can imagine in a real life where you have several policies, I mean thousands of them to enter into the system all the time. So every time you come up with a new NF, what happens? You have to come up with the same set of policies again for that new NF. But what if there's a way we can automate that in a way that we don't have to always go back and re-edit the system? Now that can be done virtually through SDN, not tested, but based on the advantages of SDN. And we can do that. And I'm going to show an architecture in a little bit. Now, the next part is the resource overhead optimization. Now, leveraging the advantages of YANK architecture. The YANK architecture is a file system. And basically, the file system runs within the kernel. Now, we can use the DPDK. I'm just going to move that off. And investigate how virtualization can be used to leverage the advantages of RTC model. Now, in the paper, they tested NFP with another architecture. I'm trying to remember the name now, which I can. They tested with another architecture, another paper that was published in 2016, OSDI, I think. And that paper actually superseded the results, in fact, way over. I didn't include that as well. Now, the reason for that is because of the race to completion model. And we have two types of model, the race to completion or the pipelining model. Now for the NFP uses the pipelining model, which basically combines everything within a container and runs it on one processor, while the race to completion model makes use of as many processors as the NFs itself. So each NF runs on one processor, which actually makes it work a lot better. And in the pipelining model, both classifier and merger can be combined to run on top of a single processor, which we can achieve that using SDN. You know, we can combine both together, we can virtualize them, and then instead of using several processors, we can just make use of one. Now, this is my proposed architecture. I don't know how to make this bigger. I don't know how to make this bigger, but I'm just going to run through what exactly it does. So here we have the VNF1, VNF2, VNF3. These VNFs are synonymous to what they have in the paper as well, like the firewall, the load balancers, and all that. Now, if we have all this, and like I said earlier, we can merge both the merger and the classifier together in one processor, so that of course we are saving hardware usage. And here we have the YANC file system, and basically what that does is it gives another view to the entire network itself, and it makes it easy to run. This is the last part. It makes it easy to run, to obtain resources from YANC as compared to just obtaining resources from the local system. So, well, I think I'm out of time, but here I have the DPDK driver. So basically what that does is it's supposed to improve or increase the amount of, reduce the amount of time it takes to have the packets being sent from the physical network elements to the actual virtual NFs as well. So, okay, I know I've spent more than enough, but there's no way I can combine the entire work of that paper in 8 minutes.
It was a really good paper. Any guys have any questions? So I have one. With virtualizing into SDN, if it's not contained into a single box, if it's spread across different boxes, are obviously going to add more latency. How do you predict that virtualization across a number of network devices will impact the processing of
Okay.
network functions?
So that's a very good question. Now, at this point, there's what they call SD NFV, software defined virtualized network functions. And basically what I'm claiming here is that we can have all that within one system, one huge server that has enough capacity, say like 256 gigabytes of RAM, for instance. Now, as long as they are running, even though it feels that they are running virtually, but they are still using the same controller. And then we can as well use a distributed controller if we feel like the controller will serve as a bottleneck, so that we can have more controllers to deal with the NFs at a fine layer of granularity, if that answers your question.
Yeah.
So the main concept here is just that it's on one entire system, and in the real world, you can virtualize more than 7 service strings. So that's not too much to put on one hardware.
Any other questions?
All right. Can you go to slide 1? I wanted to see what the name of your paper was, so I can put it on here.
Oh, sure. It's NFP.
You can just use NFP.
Yeah, NFP.
Okay.
That's the only NFP.
Yep.
All right.
All right.
Sorry.
It was great.
We're going in the order we signed up.
Just kind of going on the order that it happens to be.
What's up?
You can be.
Okay. Impact of the present. What's that? Impact. What is that? So why is this important? Okay. And I was gonna just make it a lump sum. Why is this? Why is it? Or the, yeah. Like how do you change the importance of your
My name is Tina Rose, and I am a first semester PhD student in the security program. The title of my paper is How to Undermine Your CBSP Protection, which is a critique of the paper you see below it. On Wednesday, we had talked about application issues such as denial of service, buffer overflows, SQL injections. One of the classmates mentioned a few companies such as Cloudflare and Akamai, and that's pretty much what my whole paper was about. I picked a few months ago. So if you're a small business or a small to mid-sized university, you can see our little example right here. That's one of our real IP addresses. You know, a lot of people are trying to hack us, and we're also trying to get legitimate traffic to our website as well. If you have the time, resources, and money to try to filter out that traffic, you can attempt to do that yourself. If you don't, Your next best solution is to hire a CBSP, a cloud-based security provider, also known as CDNs, like Cloudflare. Flare is a good example. They were one of the examples in this paper, as a matter of fact. How you set this up is super easy. You change your DNS record to point to your CBSP. So I got a little hypothetical example here. I chose Amazon Web Services. That's their IP address. We update our DNS, wait for it to propagate. The next person who types in uccs.edu in their web browser is going to come here first. They're going to filter out all the bad data, send us the legitimate traffic. So the question is, can we bypass this if I was a hacker? And the answer is yes, quite easily if you don't set it up properly. Remember, DNS is an optional service. It's not required. If I have your IP address, all I have to do is put that in a web browser, and I will go directly to your web server. So if I know our IP address, bypass the CBSP and go straight to the web server. Now, the solution to this problem is well known, and that's not the point of either paper, mine or the one that the previous university wrote. The solution, we'll cover it right now, is twofold. First and foremost, when you switch to a CBSP, your very first step is supposed to be change your IP address. Change it, keep it secret, only share it with the CBSP. Nobody can find it on the internet. Nobody can directly go to you. The second part of the solution, set up a firewall between your CBSP and your web server. Something as simple as IP tables. Allow anything from the CBSP, everything else deny all. That is the written solution to this problem that unfortunately 71.5% of the tested domains did not implement. So that's almost 72% of all companies who are paying for this protection can be hacked. So the point of this paper is, how can I find your IP address so that I can directly hack you? I'm going to cover only the top three in interest of time, and because they really represented the largest majority of vectors to attack you with. The subdomains, IP history, and DNS records. I kind of diverged from our instructions on this just being a paper critique because I was very curious on how to do this. So I ended up turning my computer at home into a miniature test bed, and I decided I'm going to try all of these attack vectors on uccs.edu to see what I can come up with. The reason I did that is because most of this technical detail was not in the paper. They spent all their time telling you what they were going to do and what the results were, but not how they did it. And so I unfortunately got extremely curious about this, and subdomains ended up being the easiest way to hack us, uccs.edu. You're hoping to get lucky, to get a match, that you have a subdomain that just happens to map to your web server. Because in reality, does a company, especially a small company, do they have a single web server, a different mail server, a different FTP server, a different blog server? Probably not. They might only have one server. So if I start running NS lookups on these subdomains, will I get lucky and get a match, and it just happens to be the web server? Well, in uccs.edu, it was mail. I typed that in. Within 10, 15 seconds, if I had been a hacker, I would have cracked our protection, because here are our three actual IP addresses mapped to the subdomain mail. Next up is IP history. If you did not change your IP address, first thing I'm going to do as a hacker, I'm going to go look at one of these. Can't reach that far. Got my cool little pointer here. I'm going to go to one of these IP history databases. And they were mentioned in the paper, so I decided, well, let's go to all of them. So I went to every single one, typed in our domain, was trying to see what's out there. All of them have a change history, which goes back years. Minimum was 5 years. I found others that went back well past 5 years, and I even tried a different domain just to see what would happen, and I got records from the 1970s. It was very interesting. So the information is out there. So if we, UCCS, change our protection to Amazon Web Services, the first thing I'm going to do is come here. I'm going to pull up the very first top IP address, type it in my web browser, see whether or not you changed your IP address. The final vector is in the DNS records themselves, and there's 4 attacks here. The first one is pretty rare, but it's possible if you have a human error. The top 3 A records, those are mapping to our real IP addresses for UCCS. If I change the first 2 to Amazon Web Services and I somehow forgot the 3rd record, human error, I can find it just by looking at the DNS records. Hacker, straight to your website. The second one, a lot of people don't think about, the quad A record. That's our IPv6 DNS record. Now, UCCS does not have IPv6 for the web servers. However, we had some in our DNS records. So I'm showing you an example with the DNS zones, not a 100% legitimate example, but in theory, what if I take my A record and map it to the CBSP, but I don't map my quad A record? All I have to do is take this long IP address, put it in a web browser, directly attack your web server. The next 2 almost go hand in hand. We'll look at the MX or the mail exchange records first. This is just a variation of the subdomain attack. We had 33 MX records publicly available in our DNS record online. So I looked at all 33 and I just did an NS lookup on every single server that was listed. Again, we're hoping for a match. Will one of them actually map to our web server? Now it turned out they didn't. None of the 33 mapped, but that's one possible attack vector. The final is the TXT record. For this one specifically, we're looking for the SPF text record, if you have one. That's the sender policy framework. It's used to help prevent email spoofing. So how this works, and this record, by the way, is like a paragraph long. I super condensed it to make it smaller to fit on the slide. But how this works is you list your legitimate email servers by IP address. And if any email comes out of your organization that doesn't map to one of those IP addresses, it's probably spoof or spammed email. We're just going to drop it and ignore it. So this is even easier than the subdomain attack because I have the IP addresses right here. Punched them into my web browser, was hoping for a hit to see if any of them would map up. We had 24 TXT records. Unfortunately, none of them mapped to our web server. So these particular vectors didn't do me much good trying to pretend hack UCCS. So why wasn't any of this information in the paper? The only conclusion I could come up with is because the students actually wrote a program to do all of this testing for them. So they coded up this program called CloudPiercer. It did the 3 vectors I showed you, plus 8 others I didn't show you. Didn't mention it previously, but they scanned almost 18,000 domains. Took them weeks to do the scanning. It was against 5 different CBSPs, not just Cloudflare and Akamai, but a few others. So I'm assuming they just wanted to keep their source code private. Unfortunately, I wanted more detail. I wanted to know how they did this. This application actually is available for free. So if anybody wanted to go to this website and plug in their DNS, their web server, they could see whether or not it would be something that could be hacked. And these were the references I used for my paper. Are there any questions? Yes?
There's a relatively newer area of research right now where they talk about rapidly changing IP addresses as like a security mechanism, kind of like how frequency hopping rapidly changes frequencies. An IP address scheme would randomly change over time to make the IP address kind of unpredictable. So you do your the attacker does the reconnaissance, but then by the time they go and launch the attack, the IP addresses have changed. Do you think that's a viable defense for the bypass?
To a degree, the fact that it changes in the long run, I mean, it would have to change like hourly, you know, to really stop a true hacker. If it's just changing weekly or monthly, I mean, once I get your IP address, I can do a lot of damage in that time frame. I like the theory, it's pretty clever. It would be more clever if the IP addresses were in different domains. Now, something else I didn't mention, but when I was searching the DNS records, one of those history databases gave us our whole subnet, 128.198/16. I had our whole subnet. If I wanted to, if I had the time, I'd have just brute forced every single 65,000 IP addresses. I would have scripted it, brute force attack, and have gotten our web servers that way. So changing it, sure, it's a very interesting concept. Would it be ultimately effective? I don't think so. Question?
Do you think the authors took into account that by making this tool available, they've given a easier path to finding vulnerabilities in the existing domains?
Well, you know, as mentioned in the paper, the solution's well known. So this paper really was more of a wake-up call for not only the companies, but for the CBSPs. So as the CBSP, should you have a little bit more responsibility for enforcing this? So when a customer comes to you, like let's pretend us, UCCS, and we buy your service, then shouldn't you say, go change your IP address right now, and then we will implement your service. Set up the firewall, and then we will turn on your service.
So you think the onus is on the service provider?
It's both. It's both. Unfortunately, you saw the numbers, almost 72% of people who are paying for this protection can be hacked because they didn't implement it properly, which is why we're all here getting security degrees, because they obviously need to hire immediately.
Any other questions? All right, great.
Yep, it's a PDF. You can press Shift Command F to full screen it. Select the first slide though. Yeah. All right, so I'm Gordon Brown, and I will be talking about, that's right, blind box, deep packet inspection over encrypted traffic. So what is blind box? Blind box is a system that the authors present that allows the application of traditional deep packet inspection techniques on encrypted traffic like HTTPS. And in fact, it's based fundamentally on SSL. So it's kind of got three primary parts, just to recap the paper quickly. It's a crypto system that allows an authorized third party, has to be authorized by one of the participants in the communication, to search the ciphertext for predetermined substrings. There's a network protocol that uses that crypto system, and there's an optional extension to the first two that allows full decryption of the traffic if the message contains one of the substrings. The system is described primarily as it relates to intrusion detection systems, but we'll talk about some alternative uses as well. So the implementation of the fast substring searchable encryption. Searchable encryption is a field that's been around for a while, but it's typically very slow. This works by effectively generating all possible substrings of a certain static length that's adjustable, and including those encrypted with the message. In the interest of time, I'm not going to go over all of this. The second point is a way to allow the endpoint to collaborate with the middle box, the intrusion detection system, to generate those encrypted token substrings without the endpoint knowing the list of substrings. And that's important because many intrusion detection systems expect that the endpoint won't know the rules that are being applied to it. And that's without the middle box learning the session key as well. And then the third, probable cause decryption, basically that is just a way of inserting the key, the session key, into the tokens such that if you know what the token is, then you can recover the session key. So to talk about this, in the paper they mentioned that rule generators should be separate from the middle box owners because say we're talking about HTTP, you could just make a rule that says HTTP get, and then everything will match that substring, all the gets. And now you can, if you've implemented the probable cause decryption, now you can just decrypt all the traffic. So the system includes a method to only allow rules that are signed by a trusted third party, fourth party, I guess, to be used. Honestly, though, I don't think that would actually really be relevant in real world scenarios. How often do you see an organization that is worried about implementing intrusion detection that also gives the endpoints a choice in what rules are used or not in that intrusion detection system? So, for example, why would you allow endpoints to opt out of one or more of your rules just because they aren't signed by the third party? And so it seems like in that case, you would be given the choice of accept this rule set or don't use the network. Talking about some other use cases. It's useful for parental control, they talk about that. It's useful for data encryption or data exfiltration detection by watermarks in documents. You can easily detect those with substrings. And censorship by authoritarian governments. And this is sort of a critique of this application of searchable encryption in general. While it's useful for IDS, it's very difficult to do that in a way that also protects you against, like I said, authoritarian governments. Like the Chinese government was recently found to be censoring any message that contained a number of politically sensitive keywords in the run-up to their party congress this past year. So I think that's, anytime we talk about a system like this, I think that's important to recall that this is a danger and it's a really hard problem to solve. Maybe it's impossible to solve, but we should definitely be thinking about it when we talk about implementations of systems like these. There's another critical downside to their system. While the actual search for substring matches is very, very fast compared to existing systems, it requires, like I said, one of the endpoints, it's part of the communication, to collaborate with the middle box during the connection setup. So, like I said, it also includes the encrypted substrings. And that increases your bandwidth usage by 5 times. And if you're using the probable cause detection extension, that requires including another set of tokens in order to keep it fast. And that brings your total overhead up to 10 times. That's a lot. And there's some ways that you can bring that down that I'll talk about in a little bit, but still, it's quite a bit. And during the connection setup is very heavy, and it increases both in time and in data transfer usage linearly with the number of substrings that you're searching for, such that the paper cites 10,000 rules as a typical number for a modern IDS system. Per connection setup, that takes 90 seconds and 6 gigabytes of transfer between the middle box and the collaborating endpoint. And they call this out. This you have to do some math on some other numbers they cite to really figure out. And yeah, that's another thing that I didn't love about their evaluation is they kind of glaze over the connection setup. They spend a lot of time talking about how this system impacts load times of common web pages like CNN.com, but they leave out the connection setup times. And that hurts you even more than you think, because loading CNN.com actually makes connections to 13 different domains as part of loading the ads and the videos and all this other stuff. So you get to pay that connection setup, assuming you don't, like assuming you just put this in place today. You get to pay that 90 seconds and 6 gigabytes of transfer 13 times. It seems like they're using a proxy as well that they don't really talk about, because their protocol requires both ends to participate in the blind box protocol, and obviously they didn't get CNN.com to set up a blind box enabled server. So it's kind of confusing how they got some of their measurements. So while I have a lot of complaints about this paper, it was really good. They spent a lot of time verifying that the things they did are correct. There's a proof in the extended version of their paper of the security of this protocol. They explained it very clearly, very concisely. It's a really pretty easy to read paper, even though it references some pretty complex topics. It's got a huge speed improvement, 3 to 6 orders of magnitude over existing searchable encryption systems. That said, the overhead, I think, still makes this very infeasible for real-world use. And like I said, anytime you talk about a system like this, you have to talk about the risks to privacy that still exist in a system like this. So any questions? I kind of had to zoom through the recap of the paper, so yeah.
Did you happen to examine any ways of resolving that 6 gigabyte setup?
So what that is the system uses a technique called garbled circuits to allow that computation of the encrypted token without either the endpoint knowing the plain text of the token or the server, the middle box, knowing the key. And that's where all of that comes from. So it's a little over half a megabyte per garbled circuit, and you need 1 garbled circuit per token. So if you could come up with a way of doing garbled circuits with less data transfer, that's where I would look at to address that. And I didn't have time to dive into the garbled circuits paper. Yeah.
Was that that 6 gigabytes a one-time setup for, just one time forever, and then you can use the system, or is it one time per web page or one time per day?
It's one time per SSL session. So when you basically, it's anytime you do an SSL handshake to generate that session key, you need to do the connection setup phase again.
So if you live in a rural area of town like I do, the 6 gigabytes could take like 8 hours to download.
Right. They do all of their testing under the assumption that their middle box is on a gigabit local network with the endpoint. And if that doesn't hold, then that will take a whole lot longer than that 90 seconds. Anything else?
All right.
Tried to stay on time. Hopefully it didn't get too messed up by the fact that I had to skim the paper.
Alright, so my name's Mark Stid. I am doing my presentation on the paper titled Secure Sharding Protocol for Open Blockchain. On the agenda, we're going to go over just a brief description of blockchain. If you don't know what it is, I think it's pretty common now, but we're going to go into some distributed consensus protocols. It's an important part of blockchain. It's how the multiple systems agree on what to add next to the chain. And then you walk through the Elastico protocol. This is essentially a protocol that the authors have developed to address some of the scalability issues with Bitcoin. Well, blockchains in general, but they usually compare it to Bitcoin. And then I'll briefly go over some of the testing results. Okay, so So in blockchain, with Bitcoin specifically, we have transactions come in, and they're being sorry, should be moving a little quicker. All right, whatever. So anyway, essentially a blockchain is a series of facts. All right, and they're formed. So in Bitcoin, you have transactions. These are the facts that everyone wants to agree on. Okay, and there's a header that is attached that contains some metadata about the transactions. Oh, awesome. And then the okay. So I don't know what's going on here, but so anyway, okay. So essentially, the chain is essentially it takes the hash of the first block, includes it in the next block, and it hashes together. Okay, so it's a hash chain, and the block is just the information you want to keep with that hash. Hopefully this will pick up. But so the next slide essentially goes into how's it, distributed consensus. Okay, so since there's every processor or every computer in the system has a I just want to make sure it's not gonna kick me. All right, great. So so the decentralized consensus. Every computer has a copy of the blockchain in it, right? Now, how does everybody agree on what the next set of facts should be that are added? In the Bitcoin example, they use something called Nakamoto consensus. It's named after the creator of Bitcoin, Satoshi Nakamoto. Essentially what happens is one of the processors, each processor of the transactions is attempting to solve a problem first. That's how it's commonly referred to as. It's not really solving a problem, but it's more of a race to see who can find the right random number to generate this block. And once that block of transactions is generated, then it's sent to the other processors, and they agree that that block should be added by starting to work on the following block. The consensus actually doesn't happen until after other blocks are added to the chain on top of those. So essentially, it takes about 60 minutes for the transaction to actually be committed or a consensus to happen. All right. So the major weakness with this, as you can see, if we have a small network, like 3 nodes, and a large network of, I think I have 12 there, but much larger, you only get about 7 transactions per second, and that's one of the major drawbacks of the Bitcoin environment. And in order to compete with MasterCard, you got to get 56,000, right, per second. And that's I think that was like Black Friday transaction time. So that's the major weakness with Nakamoto consensus. So there's another consensus protocol that the authors discussed called Byzantine consensus. Okay. So anyway, all of these. So essentially, instead of having everybody work on the same problem together and then everybody agrees on a certain block by working on the next blocks in the chain, everybody just talks to each other. They just say, hey, processor 1, 2, and 3, I'm processor 4. What do you think the transaction should be? And they all agree on it. In order for this to work, you need 2/3 of the processors to agree on it. Now the problem is that when you have too many, there's just a lot of communications going on. This isn't exactly how it works and how they implemented it, but it illustrates the concept of it's just there's too many messages. It takes up too much bandwidth. Essentially, it becomes too heavy. Now, the electrical protocol itself. Let's run through this real quick. So first we have to do individual processor establishment, identity establishment. I'm sorry. So one of the weaknesses of the Byzantine protocol was that you need to have everybody has to be identified, right? In order to know how to get to 2/3, you need to know who everybody is, so you can say, hey, well, 2/3 of them say yes, I agree. So you have to do the identity establishment, and that's actually one part that I had to skip over. Sorry. The proof of work. Proof of work essentially is that 10-minute time period where somebody's trying to guess a random number, and that's used in this protocol to identify to create your identity. All right. So now then the processors, after they get their identity established, they're grouped into committees. The committees then all the transactions are divided among the committees, and and then the committees agree on the blocks themselves, and then those blocks are sent to a final committee, and there's consensus. Now this last part, the random strings that are generated for the next round. Okay, so that's just brief run through. Now more visualization. Okay, so in order for the so each processor takes their public key, an IP address, their IP address, the random strings that were generated at the end of the previous round, and a nonce, as in the proof of work for the nonce from Bitcoin, and they hash it all together. The goal is to find a nonce that, when hashed with all that stuff together, comes up with a value below a certain target level. Okay, so the actual value of the hash has to be below a certain target, right? Now, how each processor is divided among the different committees is the last couple digits of their hash, right? So in this instance, we have 3 committees, the 2 here that have the numbers on them are 0, 1, and 10. Now, that's how everybody's committee is established, except for the very first one. The very first committee is established simply by the first 4, in this instance, the first four that are able to establish their identity first. So they're able to pump through all those hashes to determine their identity first. After that, okay, so the purpose of this directory is to limit the amount of communication between each of the processors. If you didn't have this directory here, the processors would have to kind of try to communicate with each other and send a whole bunch of messages across the network, trying to say, well, are you on my committee? Are you on my committee? And in this method, everybody sends their proof of work to the directory, and the directory keeps track of which committee each processor is on. And then once it sees that there are 4 processors associated with one committee, it multicasts out the list to each member of the committee, and then they form the extra committees. Sorry. All right, so this is so now we have our committees formed, and then they all listen for particular transactions that are associated with their committee. How that's segmented up, they didn't really say. They give an example of, like, for example, this committee, the last 2 digits of the hashes are 11, so all the transactions that have the last 2 digits of 11 in their code, that's the ones that they process. So each committee does the Byzantine consensus to establish, to agree on the transactions that are in their block or their shard of the overall block. Now, once that's done, everybody combines their blocks, and they send it over to one of the committees that actually doubles as the final committee. And the final committee runs another Byzantine consensus where they all just kind of agree. It's much quicker than the Nakamoto consensus. And and then then that block the set of blocks is sent out to the network so everybody can add it to their chain. So that's how they add it, and that's how they all have a kind of consensus. Now, at the same time, the final committee, each member of the committee comes up with a random number, and it's just purely for time stamping. Essentially, it prevents processors from creating an identity before the beginning of the next round, essentially. So this string is used at the beginning of the hash when I mentioned the random number. Let's see. So from a scalability standpoint, so essentially the authors rented a bunch of servers from Amazon, and so they ran it in a couple runs here. We had 100 nodes, 200 nodes, 400 nodes, 800 nodes, 1600 nodes. The committee size was of 100. Now you can see over here we have the time, so about 600 seconds, which is about 10 minutes. So for about this is this light gray is the committee formation time. That's where everybody's trying to generate their proofs of work, and then the formation of the committees themselves, where they're talking to the directory committee. And that only takes about 10 minutes on every single instance. So on every implementation they tried, because they're done in parallel, essentially, right? I'm sorry, no, that's not done. Everybody does it at the same time. The consensus, there's the darker gray up there, that has that's where the real improvement comes in, because that's the part that's done in parallel. Instead of having 1,600 nodes all talking to each other at the same time, which would take a very long time to send all the message through whatever protocol they're using. They'd segment it up into each committee, and that's where the real efficiency improvement comes in. And as you can see, if you have 100 nodes, 100 processors in a committee, you have essentially, for every committee, you get another block. So 16 committees, you get 16 blocks. And that was kind of their goal to begin with. Brief summary, discuss blockchain briefly, went over some consensus protocols that the Elastico protocol uses, step through the actual Elastico protocol, and review the scalability testing results. All right. Any questions?
Okay, so I'm not an expert, but I know that the normal Bitcoin protocol is vulnerable to attacks where if you control greater than 50% of the pool, you can control what transactions get accepted.
Yeah.
Is this similarly vulnerable to controlling 50% or more of a committee?
Yeah, that's what the so they mathematically prove use probability to prove that as long as a sufficiently large number of nodes, so as long as there's sufficiently a large number of everybody, that the probability of having, let's say, there should be less than one fourth of that, essentially, is what the probability of having malicious users are. And now, if it does get above actually 1/3, then you start to have issues. That's where, because the Byzantine consensus, I don't have the slide in here. The Byzantine consensus essentially is so if you have 3 processors, right? So they all have to agree on something, and one says one thing to one, and then says another thing to another one. It prevents anybody from making an agreement. Now you need a 4th one in there so that you can say, well, there's at most one malicious processor. So then you can see that, okay, so the yeah, I'm not going to say. So at any rate, you need 3 times the number of expected Byzantine processors in order to be able to combat that. I danced around that. I'm sorry.
Okay, so you start seeing problems when about 1/3 of the nodes are.
Yeah, that's essentially what it is.
Okay.
It's about 1/3. Once you get past that, then you can't have an agreement in the Byzantine consensus. Anything else? All right.
All right.
What was your name of your paper?
The secure sharding protocol. Just put sharding.